So what's next here? So now we want to improve the system, the multi-point network, right? And so that's where AIRMAX AC comes in. Now, we've had AIRMAX AC under wraps for a while. The first products are probably going to ship. We're shooting for the end of the year. It might be early next year. I'm going to give a very abstract overview of some of the features and benefits of it. So one of the big game changers in AIRMAX AC is we now have a dedicated processor for the AIRMAX protocol. So the AIRMAX protocol in the existing technology and existing products, it's all based on software. All the timers, all the scheduling, it's all software based, and so it's much slower. Now we have a dedicated processor, so it's going to be much faster, and you're going to see improvements in scalability and latency. The next thing we have is advanced products. We have a whole new UI, more features. We have new base station products that are going to be, I think, very compelling. And my favorite feature, and we've been working on this feature for a long time, I think it goes back 4 or 5 years ago, is we're introducing technology. It's essentially active frequency filtering. And I'm going to talk about that right now. So WISP networks, they operate in the unlicensed bands, right? And the unlicensed bands are getting more crowded and more crowded. And so the key to robustness and capacity, scalability, is our ability to filter out this interference. And there's different ways you can filter out interference. The first way, or the most common way WISP figured out 10 years ago, was using directional antennas. If you could focus where the antenna hears, you could essentially spatially filter out a lot of the noise or a lot of the signals you don't want to hear. Another way is to use, you can filter in the time domain using scheduling techniques like polling and like our AIRMAX does. Now, what we've learned and what I've learned in the lab over the last several years in dealing with customers, these are good solutions to filtering out noise, but they're really just Band-Aids for the real problem out there. And so the real problem is frequency, is frequency and selectivity of these radios. And so we're going to attack this problem at the source. And you attack it at the source with active frequency filtering. So I'm going to take you guys back a little ways. There was one of the first chipsets, it was in 802.11 that became popular, was this InterSIL 2 and InterSIL 2.5 Prism chipset. And the first product I designed when I was starting Ubiquiti were these Super Range 2 and Super Range 5 Atheros mini PCI cards. And we sold a lot of them. But there was a pattern in the Super Range 2 cards we were selling. Anybody that replaced their Prism 2 card with a Super Range 2 card in an access point mode, they would always send it back to us. And they'd say, hey, this card sucks. You know, it can't operate where my Prism card operates. And you know, my background is in RF engineer, RF circuit design. And so I was doing all kinds of crazy things in front of the Atheros chip, fixed filtering and attenuating and changing the low noise amplifiers. And I was working with customers to send them back and forth and try them. I said, try this design, try this design. And nothing I did helped. And it's interesting, right? Because the 802.11b was, it wasn't even OFDM. It was 1/5 the speed, 1/6 the speed in the lab as these new cards. Yet these Atheros radios were just not performing well in these 2.4 noisy environments. And there's a reason why. The InterSIL radio, it was a good radio design, designed for a commodity application, but it was a super heterodyne receiver. It had 2 intermediate frequency stages. It had SAW filtering off chip, it had a lot of design features that gave it great selectivity. So what is selectivity? The selectivity is the radio's ability to capture its signal and ignore other signals, right? Now, once the Wi-Fi industry evolved, it became about cost. It became about integration, low power. And so all these off-chip components, which made the radio performance, the selectivity really great, were kind of cast away for these other purposes. And so these Wi-Fi chips today, they're not really capable of handling an outdoor high-density RF, high-power RF environment. Now, they work great in indoors, right? But once you get them outdoors with interferers, they don't have selectivity. The selectivity degrades very quickly. And that's why sometimes you might notice, even though you're using non-overlapping channels, your network still has degradation. And that's because these chips just can't handle high RF power. If it's adjacently or even very far away from your signal, it will just swamp out the receiver's ability to select the signal of interest. So to illustrate this, let's look at a low-energy RF environment. And to the Wi-Fi receiver, it can very clearly see the individual channels. And if it's operating on one of these channels, it's able to select and communicate on that channel effectively. And if there's a weak interferer on a neighboring channel or on a distant channel, no problem. It will still be able to operate optimally. Now, once you go outdoors, once you have directional antennas, focusing high energy density, then everything breaks down. Whether you have an interferer next to your signal, whether you have it 200 megahertz away, 300 megahertz away, if it's strong enough, either a single signal or a combination of signals, it will just swamp out the receiver. And so the Wi-Fi receiver, or the 802.11 silicon, doesn't see clear, discrete channels anymore. It just sees a blob. It's almost as if you don't have overlapping channels, non-overlapping channels anymore. It's almost as if any channel is part of the blob, and it's just all one RF space, right? So that's the problem we're running into right now. And some people, I think, can see it right away, right? If you improve your spatial filtering and you put metal shields and things like that, you can improve the problem because you're presenting a weaker RF ambient noise environment. So the 802.11 silicon can operate optimally. But in a lot of cases, you can't. So what's the solution to this? So how do we improve the selectivity of the radio? So one obvious way is we just put a filter in front. Say your radio is operating on 5,500 megahertz. Let's put a brick wall filter right in front of the radio. Now, the problem with that is if you put a fixed filter in front of the radio, it won't be able to operate on any other channels. So once you deploy it on that frequency, you're done. You're not going to be able to change it. Now, the second problem, more importantly, is a small channel at 5 gigahertz has a very tiny fractional bandwidth. And if you want a brick wall filter at a small fractional bandwidth, you need a huge, what they call Q in the filtering world, and it would amount to a giant filter, which is impractical for most of these applications. So what do we do? So what if there was a way where we could take the ambient RF environment, the 802.11 silicon sees, the Atheros chip sees, and what if there's a way to make it look like a low RF power ambient environment? Then the chipset would be able to operate optimally. It would have great selectivity, and a lot of the noise problems you guys are seeing in the field would be gone. It'd almost be like a return of the intercell Prism radios, but at much, much higher speeds, okay? So that's what we've been working on for a long time in our lab. And we're calling this technology AirPrism. And it sits in front of the etherosilicon, totally agnostic, but it's actually a tunable active filter. So it works in kind of, it's paired to the 802.11 silicon, and it moves with it. So no matter what channel you're operating on, we're essentially applying a brick wall filter. And so you can think of it, we're transforming the RF ambient environment to a low power RF ambient environment, so the Wi-Fi chipset, in this case, can run optimally, the selectivity. So I believe, just like NanoStation changed the industry, just like AIRMAX elevated it again, I believe moving forward, AirPrism is going to be a game changer for this whole market and this whole industry. And if you want to check it out, we have one product today we're shipping with AirPrism technology, and that's the, we've disguised it. It's called the UAP Outdoor Plus. And if you want to kind of get a glimpse, I highly suggest you check out that product and run some tests on it. That design was much easier because it was at 2.4 gigahertz. So we only have to apply filtering over essentially 80 megahertz of spectrum. In the 5 gigahertz case, we had to tackle a few hundred megahertz spectrum. So the bandwidth's much greater. The design was much more challenging, but it's getting very close. It's going to be shipping in AIRMAX AC products next year. So that, I guess, concludes the show. And thanks, everybody, for coming out. So Ben, JT, we're done?
If you have any questions, I'm up here. So you can come up. You want to sign up to get iPads. So.
Yeah, thanks everybody for coming.